When they're not, it behaves another. All righty? Questions? Comments? Tell you what, let me show you just to, I'll be the first to admit these things are difficult to visualize. So this is a simple little animation just to show you what we're talking about here. No sound on this one. Here's the rigid body flying around in space. It has a center of mass. That's what we're going to choose in this discussion as the origin of the body coordinate system. The angular velocity vector goes through that, points off in some direction. The body coordinate system is attached to the rigid body and rotates with it. All right? I mean, that's what you're talking about. I mean, it's kind of weird, it's kind of out there, but that's what's going on here. Okay, questions, comments? All righty then. There was a point I was going to make. No, that'll do. All right. That is the end of the video segment number 1. And what I'd like to do now is begin video segment number 2. Let me bring this one down and send this one away. Okay. All right. Let me write this out for you. Sorry, I've got a little bit of repetition here. Okay. The situation is that once we choose the origin of the body coordinate system and its directions, then all of the little particles, m sub I, that make up the object, each of which having its own linear velocity, all right, are all of this, as you'll see in a moment here, the position of all the points, the angular velocity of the entire rigid body, and the angular momentum of the rigid body are all defined with respect to the body coordinate system. That is, all of these key concepts we're speaking about flow from your choice of body coordinate system origin and axis directions. Fair enough? Let me just see here. Yeah. Okay. So, point O I speak of is the origin of the body coordinate system that we have chosen. All right. Now, I'm just going to go very quickly through a derivation that's in your book You know, that big fat thing that sits on your shelf and serves as a paperweight? Yes, sir.
Both your inertial frame and your body frame have both as
Oh, I'm sorry. Yeah, I'm sorry. This is supposed to be little o.
not at all clear which point we're not.
Ah, thank you. Okay. First off, it's not capital, just to be clear, this is supposed to be capital O. This is supposed to be lowercase o, to jive with the book. And the one I speak of here okay? Then the velocity of any of these, of all these individual points can be found by this simple expression here that you're way familiar with. So, this familiar expression, as I was saying, this is a derivation of the moment of inertia matrix. This is intended to answer the question, where does that come from? This is described in your book, so I'm not going to belabor this here, but it goes like this. This is essentially the definition of the linear momentum for the entire rigid body. And simply expanding this, that's the task at hand. Now, let me just say there is a little known vector identity that you may well not just happen to remember. Make sure I got this right. Which yields the following. Hang on. Times omega minus r sub I dot omega times r sub I. Okay, in which all right, I'll give you a chance to get that down. Any questions on that? All right, and again, this is a derivation. It's not something you have to commit to memory, but at least once in your life, it'd probably be good for you to go through it, work through this, just to convince yourself that this all makes sense. Basically, we have a formula for the linear velocity of every point. We use that to expand the definition of angular momentum. And with a vector identity, we can rearrange it in such a way that we get the following. Now, what is this exactly? A vector, a matrix, a vector, okay? The angular momentum is expressed as a vector. It's got three components in general, as does the angular velocity. And basically, we see that there is a matrix in between that links these two. Questions about that? Now, if you go through that, this is what comes out the other side. Ugh. All righty. Now, let me just prepare you here. I mean, you can take your time, copy this if you want. This is in your book. All right. If you should feel free to read this and copy it out of the book as well as here. But what we're going to do today, and probably tomorrow as well, is we're going to talk through these. We're going to talk through this expression to examine this in detail. What is this matrix? What does it mean? What do the components do? And so forth. All right, before we get started, any questions? Anybody kind of taken aback by the nastiness of the expression, or is it clear enough? I'm assuming you've seen this before. All right, well, let's start going through this. Now, let me just say this expression was true for one choice of origin of the body coordinate system. Had we chosen the center of mass, a different one, angular velocity would have been the same. The numbers that come out of this expression would be different, as would the angular momentum as well. Everybody clear? Yeah, Elise.
Yeah, in the bottom right-hand corner of the matrix, the ZC term, should that be a y-squared?
I'm sorry, which one are you talking about? Oh, yeah, thank you. Very good catch. This is wrong, is it not? X by, yes, thank you very much. Let's just fix that right now. This, Elise, very cleverly picked up an error. Thank you very much. This last term should read sigma, the summation of m sub I, x sub I squared plus y sub I squared. Fair enough? Okay, thank you. All righty, questions, comments? Okay, let's start working our way through this. First off, let me give you some kind of big picture stuff, and then we're going to go through the particulars. First thing is that what the moment of inertia matrix is, intrinsically, is a measure of how the mass of the rigid body is distributed. Okay? Where is it? And in cases where the object is of uniform density, then it follows that it's a statement about how the geometry is distributed. Okay? But what it really measures is where's the mass, and how's it distributed? All righty? Okay, that's number one. Okay, how about it? Gentleman in the back row there, what's your name? Larry, can you read this?
Yeah.
Perfect. Okay. And then the last one is all right, the last thing is that the moment of inertia matrix is defined with respect to the point and the direction of the body coordinate system. What that means in practical terms is that you have an object, okay? Just as in the scalar case, it's not sufficient to say what is the moment of inertia of this object. Not enough information. You have to say, here is a body coordinate system. Here is where its origin is, and here's where its direction, X, Y, and Z axes are, and then and only then can I tell you these numbers. Everybody follow me? Okay? So,